Imagine this. It's morning, you're making breakfast, maybe some crispy bacon, and those eggs just glide effortlessly from the pan onto your plate.
Yeah.
No scraping, no scrubbing. It's that familiar comfort of nonstick cookware, something, well, many of us take for granted.
Definitely.
But what if that incredible convenience comes with a hidden cost?
Yeah.
Maybe raising some serious questions about safety and, the environment.
It's a really critical question right now. For, about 70 years, materials like polytetrafluoroethylene, PTFE, you probably know it from brands like Teflon.
Sure, Teflon.
They've been the undisputed gold standard for nonstick surfaces, and their effectiveness is, well, it's undeniable.
Right.
PTFE offers exceptional resistance to chemical attack, corrosion, heat. It's why it became so widespread in the first place.
And this is where things get a bit complicated. This PTFE, it belongs to a larger family of chemicals, the per and polyfluoroalkyl substances, or PFAS.
The forever chemicals.
Exactly. You've probably heard them called that. And for good reason, they're incredibly persistent. They don't really break down easily, not in the environment, not in our bodies. And that persistence has been linked to a growing list of health concerns, things like cancers, liver issues, developmental problems.
Precisely. So for this deep dive, our mission is to really unpack why finding alternatives to these traditional PFAS non-stick coatings is, well, it's not just a scientific challenge, it's becoming an urgent societal necessity.
Okay.
Then we're going to dive into some truly groundbreaking new scientific approaches, focusing on a really fascinating paper by Samuel O. and his team.
Right.
We'll explore the specific problem they're tackling, their surprising results, and what this could all mean for the future of our kitchens and, frankly, many other industries too.
All right, let's start at the very beginning then. How does nonstick cookware even work? Like, what's the role of these PFAS chemicals in that sort of initial magic?
Okay, so when you put food into a bare metal pan and turn on the heat, food actually sticks for a couple of reasons. Metals have what scientists call high surface energy. Basically, the atoms on the surface are really eager to bond with other molecules, like your food. Plus, metal surfaces, they look smooth, but microscopically, they're actually quite rough. So as Professor Kevin Golovin from the University of Toronto puts it, you're basically filling in all the topography of the cookware with food.
Gotcha. So the food gets stuck in the tiny valleys.
Exactly. So to make a pan nonstick, you apply material that does the opposite. This coating, it fills in those microscopic nooks and crannies, and it solidifies into this incredibly smooth, inert surface.
Inert meaning it doesn't react.
Precisely. And PTFE is a wonder material for this because it's built from these long chains of carbon atoms, each strongly bonded to fluorine atoms.
Okay.
These carbon-carbon and carbon-fluorine bonds are among the strongest known chemical bonds, so they create a surface that just doesn't want to react with food molecules.
So the food can't really grab onto it.
Right. Food can only weakly adhere through these fleeting things called van der Waals forces, tiny temporary attractions that are easily broken. So liquids in food just glide around.
But this wonder material, it's facing a lot more scrutiny now, isn't it? And regulations, too.
It really is. Minnesota, for example, just became the first U.S. state to actually ban the sale of PFAS-containing products, and that includes cookware.
Wow. Okay.
And other states are considering similar laws, as is the European Union. France has a PFAS ban coming in 2026, although, interestingly, cookware is currently excluded there.
Excluded? Why?
Seems to be due to pushback from major French manufacturers, like Tefal.
Industry influence.
And you're right, the industry is certainly pushing back more broadly. The Cookware Sustainability Alliance, an industry group, has actually sued Minnesota over its ban.
On what grounds?
They argue that fluoropolymers like PTFE are safe and have been approved for food contact use by regulatory bodies like the US FDA and the European Food Safety Authority.
So it really highlights this tension, doesn't it, between kind of established practices and the evolving science?
Exactly.
So how do we, as listeners, make sense of that? The industry says it's fine, but we hear all these links to health concerns. Where did this controversy even start?
Well, the concerns about PTFE cookware safety actually started over 2 decades ago. The big issue back then was PFOA, perfluorooctanoic acid.
Okay.
It's a specific PFAS molecule they used as a processing aid when making PTFE. PFOA was linked to cancer, and thankfully, PTFE makers phased it out by around 2012.
Right, so new nonstick pans today should be PFOA-free. You see that label a lot.
You do.
But does PFOA-free really mean PFAS safe? Is that the end of the story?
That's the crucial question, isn't it? Phasing out PFOA was definitely a step forward. But critics, like Gillian Miller from the Nonprofit Ecology Center, argue that PTFE coatings aren't necessarily inert or completely safe just because they're PFOA-free.
Why not?
Well, the problem is, if you overheat the pan, typically above 260 Celsius, that's about 500 Fahrenheit.
Which you could easily do if you leave an empty pan on high heat, right?
Easily. Or even if you get deep scratches in the coating, that can degrade the PTFE.
Right.
And this degradation can release smaller PFAS molecules into the air and potentially into our food.
Okay.
There was a study in 2022, for instance, that showed just a single crack in a coating could release thousands of these tiny PTFE particles.
Thousands. Wow. And are there direct effects from these fumes or particles?
There can be, though they're uncommon. There's a temporary flu-like condition called polymer fume fever, or sometimes Teflon flu, from inhaling the fumes.
What?
And those same fumes are actually fatal to birds, which is why you should never keep pet birds in the kitchen when using nonstick.
Good to know.
Now, these human cases are rare and usually tied to extreme overheating, but it definitely raises questions. As Miller points out, the amounts might be low and not a concern, but there's no simple answer.
Right. It's not black and white.
And there's another critical piece here, beyond just using the pan. It's the entire product life cycle.
What do you mean?
Even if the final pan you buy is considered inert under normal use, the manufacturing process itself often still uses other PFAS molecules. Things like Gen X replaced PFOA.
Okay. And are those safe?
Well, the full toxicity risks of these newer manufacturing aids aren't entirely known yet, and their use definitely leads to ongoing air and water pollution near manufacturing sites. So as Miller highlights, just focusing on the finished product is a significant oversight. You have to consider the environmental footprint from start to finish.
Okay, so the whole PFAS safety debate is clearly heating up. People are looking for alternatives naturally. The most common one you see is ceramic cookware. What exactly is that?
Yeah, you see it everywhere. But the label ceramic is actually a bit of a misnomer.
How so?
It's not conventional ceramic like, pottery or tiles. These coatings are typically a siloxane-based network. Think silicon and oxygen, similar to glass, but with organic methyl groups attached. They often add inorganic particles like silicon dioxide to give it that enamel-like look.
So it's more like a special kind of hardened gel.
That's a pretty good way to think about it, yeah. A sol gel coating.
And how do they perform? I feel like I've heard people say they don't last as long as Teflon.
User reports often do say they lose their nonstick properties faster. The scientific reviews are actually quite mixed.
Wow.
Yeah, one study from 2024 found ceramic held up better to heat in mechanical wear. But a more recent preprint study, and this one's interesting, they simulated years of cooking by just making pancakes over and over again.
Okay.
They actually found that Teflon still outperformed the commercial ceramic coatings they tested in terms of both stickiness and wear resistance, though some ceramic options did come surprisingly close.
So still maybe not quite as good overall.
Potentially, and here's a really crucial point for anyone shopping. Ceramic can be a very misleading term.
Oh.
Some pans advertised as having ceramic coatings can still contain PFAS.
Wait, really? How?
The PFAS might be attached to the ceramic material somehow, so manufacturers can label them Teflon-free or PFOA-free, which is technically true.
Because it's not that specific PFAS.
Exactly, but they might still contain other fluorinated compounds. So your best bet, if you really want to avoid PFAS completely in nonstick, is to look specifically for a label that says fluorine-free.
Fluorine-free. Got it. That's a key tip. What about just avoiding nonstick coatings altogether, like the old school pans?
Absolutely. Many professional chefs, for instance, swear by stainless steel, carbon steel, or good old cast iron.
Right.
They're incredibly durable. They can handle high heat metal utensils, the works.
Well, they stick more, don't they?
They can, yeah. The trade-off is that they require a bit more technique and maintenance. You need proper preheating, often oil, maybe seasoning for cast iron and carbon steel to minimize sticking.
Okay.
But, from an environmental standpoint, an uncoated pan might actually be the best choice. It can literally last for decades.
Whereas any nonstick pan, no matter the coating, eventually wears out and becomes trash much sooner.
Exactly. It's got a limited lifespan.
Which brings us back to why the science is so important here.
Precisely. This is why the scientific community has been racing to find a better way. And that leads us right into the core of the new research we're exploring today. The challenge: developing truly sustainable materials that offer comparable oil repellency to traditional PFAS, but without those environmental and health risks.
It sounds like a huge ask.
It is, because even the shorter chain PFAS, things like C4 and C6, which were introduced as safer alternatives, well, they still have toxicity concerns, like liver toxicity, and they often don't repel liquids quite as well as the older long-chain ones.
And regulations are catching up even with those, right?
They are. There's an EU-wide regulation on all PFAS currently under review, so the urgency to find totally new solutions is really clear.
Okay, so enter the paper by Samuel Aw and his team. How did they approach this? What was their inspiration?
Well, they took inspiration from something called perfluoropolyethers, or PFPEs. You can think of these as sort of like polymer brushes. Yeah, like molecules sticking up from a surface. These PFPE brushes have incredibly short PFAS chains, like just C2 or C3, linked together by an ether backbone that's an oxygen atom link.
Okay, C2, C3. Very short.
Very short. And because the backbone is flexible, these tiny fluoroalkyl chains can actually reorient themselves towards the surface. They kind of wiggle around to maximize the number of those crucial CF3 groups pointing outwards.
The CF3 groups being the key part for repellency.
Exactly. That maximizes the omniphobicity, repelling both water and oil, and achieves performance similar to the short-chain C4 or C6 PFAS.
And the thinking was, if these degrade, they make less harmful stuff.
That was the initial idea, yeah. If TFPE brushes degrade, they'd mainly produce these ultra-short C2, C3 PFAS, which are considered less harmful, less bioaccumulative than the longer chains.
But there was a catch.
There was. Even PFPE still contains a substantial amount of PFAS overall, and a lot of that fluorinated polymer doesn't even end up right at the surface where the repellency actually happens.
So it's wasted fluorine.
Essentially. The researchers called it excessive PFAS emissions without notable benefit. It was still using a lot of fluorine for maybe not enough payoff at the very top surface.
Okay, so PFPE wasn't the perfect answer either. What was the breakthrough idea from Aru and his team then?
Their brilliant idea was this. They realized you don't actually need those long or even short fluoroalkyl chains to get extreme repellency. Their novel method essentially fletches a different kind of polymer brush.
Fletches, like on an arrow.
Exactly like that. They used liquid-like polydimethylsiloxane, or PDMS, brushes that's a type of silicone polymer.
Okay.
And they fletched them with single perfluorocarbons, specifically just the single NACA-CF3 group.
Just one CF3 group, not a chain, just the end bit.
Precisely. Just that tiny trifluoromethyl group. It sounds incredibly precise, and it is.
Why focus on just the single NACA-CF3 group? What's special about that?
Well, the beauty of a single NACA-CF3 group is that it's considered the least toxic of any PFAS molecule.
Least toxic.
Yeah. It's apparently easily excreted from mammals, doesn't bioaccumulate, and poses very low toxicity to aquatic life. In fact, you might already encounter it without knowing.
Where?
It's used in some FDA-approved pharmaceuticals, in materials for solar cells, even in dyes for fluorescence microscopy. So it's a molecule we actually have a decent amount of experience with in other very different applications.
That's fascinating. Okay, so if it's less toxic and already used elsewhere, how do they actually make these CF3 fletched PDMS brushes? How do you stick just one CF3 group on there?
It's a multi-step process. First, they grow these PDMS brushes directly onto the surface they want to coat.
Okay.
Then they treat the surface with oxygen plasma. Think of plasma as this highly energetic gas.
Right.
It chemically changes some of the methyl groups, the CH3 groups on the PDMS surface, into new reactive sites called silanols, SiOH groups.
So it creates little anchor points.
Exactly. Tiny, eager anchor points ready for the next step. Finally, they introduce a specialized chemical, which they cleverly called a CF3 fletching agent. Specifically, it's 3-valent-3-valent-3 trifluoropropyldimethylchlorosilane. Rolls right off the tongue.
Not quite.
No, but this agent reacts with those silanol anchor points and replaces them with one or more of those single NACA-3 groups.
And they could confirm it was just single groups, not longer chains forming by accident.
They did. They used a technique called XPS, X-ray photoelectron spectroscopy, to analyze the surface chemistry, and it confirmed that only single NACA-3 groups were present with no signs of longer fluorocarbon chains.
And the fletching name came from how they look.
Yeah, apparently the molecular distribution of these groups on the flexible PDMS backbone resembles the feathers on an arrow shaft, orienting themselves for optimal repellency.
That is incredibly clever molecular engineering. Okay, so let's talk results. This is where it gets really interesting, right? How did these CF3 fletched PDMS brushes actually perform? Did they repel oil well?
The performance was remarkably good. These new brushes consistently showed higher advancing contact angles for various oils with low surface tension, things like heptane, octane, decane, compared to just plain PDMS brushes.
Higher contact angle means more beating up, less spreading.
Exactly. That's what you want for repellency. And what's really significant is that this performance was very similar to that of the traditional short-chain C4 and C6 PFAS materials.
Okay, so comparable performance,
Yeah.
but here's the kicker, right? The fluorine content. What did they find there?
This is the real game changer. Despite getting that similar repellency, the CF3 fletched PDMS brushes achieved it with approximately 8 times lower fluorine surface density compared to 6 PFAS self-assembled monolayers, or SAMs.
8 times less fluorine.
8 times less than C6. And get this, an astounding 40 times lower fluorine surface density compared to a C4 PFAS surface that offered similar repellent properties.
40 times. That's huge.
It's massive. It means you need significantly less fluorine to get the same nonstick or repellent effect, which translates directly to potentially far less fluorine being released into the environment over the product's life cycle.
Wow. And it gets even better if you think about what happens if these materials do eventually break down, right?
Yeah.
What about the degradation byproducts?
That's another key advantage they highlight. If these CF3 fletched PDMS brushes were to degrade, the expectation is that they would likely degrade solely into trifluoroacetic acid, or TFA.
TFA. It's that bad?
Well, TFA's long-term environmental accumulation is an ongoing area of study and some concern. However, it's generally considered non-bioaccumulative in organisms, meaning it doesn't build up in the food chain like longer PFAS, and it's thought to be significantly less toxic than the longer-chain PFAS compounds we're trying to replace.
So a potentially much safer breakdown product.
Exactly. It addresses a major environmental worry about these forever chemicals sticking around and building up.
Okay, what about how liquids move on these surfaces? Is it just about beating up, or do things actually slide off easily too?
Good question. They looked at that too. They found that even though the CF3 fletched brushes had slightly higher static friction, meaning it takes a tiny bit more initial force to get a droplet moving, they exhibited significantly lower dynamic friction for these low surface tension liquids.
Lower dynamic friction, meaning once it's moving, it slides more easily.
Precisely. So once an oil droplet starts moving, it slides off much more readily. That's really crucial for applications where you have continuous liquid hitting the surface, like coatings, enzyme pipelines, maybe even self-cleaning surfaces or windshields.
That makes sense. Didn't they do some kind of spray test to simulate that?
They did. To test real-world effectiveness under continuous exposure, they ran a spray test. The CF3 fletched PDMS brushes, much like the standard C6 PFAS surface they compared it to, managed to maintain drop-wise repellency for all those low surface tension oils.
Meaning the drops just kept beating up and rolling off.
Exactly. In contrast, a regular PDMS surface without the fletching became completely wetted, covered in a film of oil. So it's a strong indicator that this new coating could hold up well in real-world conditions with continuous liquid exposure.
What's really striking here is how broadly applicable this seems. It's not just for like specialized lab equipment, is it?
Absolutely not. They showed the coating can be applied to a variety of common materials, polyester, nylon, even aluminum, just by using an intermediary silica layer to help it stick.
So potentially clothing, packaging, industrial parts.
Potentially, yes. And it also works well on rough or porous surfaces. They tested it on stainless steel mesh and found it significantly enhanced resistance to liquids soaking in, performing similarly to C4 PFAS in that test. That opens doors for many industrial uses beyond just flat, smooth surfaces.
And let's bring it back to something maybe more relatable for you listening. Textiles. What happened when they put this on fabric?
This is a great example. When applied to fabric, these CF3 fletched PDMS brushes significantly boosted the oil repellency. They achieved a grade 6 rating on a standard test.
What does grade 6 mean?
It means the fabric could resist wetting by oils all the way down to decane, which is quite a challenging oil to repel. For comparison, fabric coated with just regular PDMS only scored a grade 4.
So a big improvement.
A really big jump. This has massive implications for things like waterproof breathable jackets, oil-resistant workwear, maybe even upholstery or carpets. Imagine outdoor gear that truly repels everything, water, oil, dirt, without needing traditional PFAS.
And that would be incredible.
Yeah.
But How durable is it? That's always the question with new coatings, especially for clothing or cookware.
Crucial question. The researchers did put these coatings through some rigorous durability tests.
Yeah.
They held up pretty well. They remained stable after being heated to 100 degrees Celsius and even 200 Celsius. That's nearly 400 Fahrenheit for 72 hours straight. So good thermooxidative stability.
Okay, handles heat. What about chemicals or physical wear?
They also tested chemical stability. The coatings resisted acidic conditions down to pH 3 for 24 hours and actually outperformed C4 PFAS in that specific test.
Better than C4 PFAS. Interesting.
Yeah. And they showed similar stability to both C4 and C6 PFAS when blasted with water jet impacts, simulating physical wear or maybe harsh washing. So the initial durability data looks quite promising, suggesting they could stand up to real-world use.
Okay, so this technology looks incredibly promising on paper and in the lab. But what are the hurdles? What are the challenges to actually getting this stuff into our homes, onto our jackets, maybe even into our pans? Scaling up production is always a big one, I imagine.
You're absolutely right. Scaling up is the next major challenge. Moving from lab-scale synthesis to industrial manufacturing always involves hurdles.
Like what, specifically?
Well, they might need to figure out how to integrate things like inline plasma treatment systems into existing manufacturing lines efficiently, or perhaps develop new ways to create the PDMS polymers with the fletching agent already attached, though they mentioned steric hindrance, basically molecules getting in each other's way could be an issue there.
Okay.
And also applying this coating uniformly to really complex non-flat shapes like the inside of a pipe with lots of bends could be trickier than coating a flat piece of fabric or metal.
Right, practical manufacturing challenges. And we have to circle back to this TFA question, the trifluoroacetic acid degradation byproduct. You said it's less toxic, but is there still an environmental concern about it building up over time?
That's a very fair and important question. The long-term environmental fate and potential impact of TFA is still an active area of scientific debate and research. It's found globally, even in remote areas.
Okay.
However, the researchers here put the potential emissions from a product using this specific technology into context. They estimated, for example, the maximum amount of TFA that might be released from a single waterproof jacket coated with this material over its entire lifetime.
And what was the number?
Around 65 milligrams per jacket,
Yeah.
which sounds like, well, it's hard to know what that means on its own.
Right. Is 65 milligrams a lot or a little?
Compared to current major sources of TFA in the environment, it seems negligible. They compared it to the TFA emitted from just over an hour's worth of leakage of HFC refrigerants, common coolants from a typical car's air conditioning system.
Wow, just an hour of AC leakage.
Yeah. Or compare it to the estimated annual TFA emissions just from pesticide breakdown in a country like Germany. That amount is equivalent to the potential emissions from something like 9 trillion jackets coated this way.
9 trillion. Okay, that puts 65 milligrams in perspective.
It really does. So while TFA itself is something to keep monitoring, the contribution from this potential PFAS alternative appears vanishingly small compared to the big sources already out there. It's about finding significantly better solutions, even if they aren't absolutely perfect, and this looks like a huge step forward.
Okay, so wrapping this up, what does this all mean for you, our listener? Let's distill a couple of key takeaways from this deep dive.
First, I think it's abundantly clear that the traditional PFAS coatings we've relied on for decades pose significant, well-documented environmental and health concerns. That's driving this urgent global need for safer alternatives in so many everyday products, from the pans in your kitchen to the jacket you wear outdoors.
Absolutely. Second, this nanoscale fletching approach, developed by Samuel All and his colleagues, using those single CF3 groups on PDMS brushes. It offers a genuinely promising solution. It manages to achieve high-performance oil repellency,
Comparable to existing PFAS.
but with drastically reduced fluorine content. We're talking 8 times less than C6 PFAS, an amazing 40 times less than C4 PFAS for similar properties. And crucially, it results in far less harmful degradation products if it does break down.
And maybe a final point. This groundbreaking research fundamentally shows us that high-performance liquid repellency isn't inherently tied to needing those long, persistent PFAS chains.
Right, we don't need all that fluorine.
Exactly. It proves that through smart molecular design, we can achieve the performance we want more sustainably. This really opens the door for a new generation of high-performing materials across so many industries. paving the way for a future with much less reliance on these forever chemicals. It's about clever chemistry, really.
Yeah, what really stands out to me is just that sheer ingenuity of molecular design and engineering. It's kind of a powerful reminder, isn't it, of how precisely we can now manipulate materials way down at the nanoscale
Yeah.
to try and solve some of our biggest environmental and health challenges. So maybe next time you're shopping for a new pan or maybe a waterproof jacket, perhaps you'll look a little closer for that fluorine-free label we mentioned and just, consider how this next generation of smart materials might start reshaping the products we interact with every single day, hopefully making them both high-performing and safer for us and for the planet.